Oh, thanks, Matt, and thank you very much, first of all, to Marsha and to the Brahman Association for the opportunity to come and talk to you today. It's always good to have the science session, if you like, straight after lunch when you're all ready to go. So hopefully we'll try and get through it, and you'll still be awake at the end of this. But so just to start off with, I just thought I'd give you a little introduction to Neogen. I think a lot of you probably use this for genomic testing, but you might not be all that familiar with actually the organisation itself. So Neogen ourselves, we are a large kind of multinational, big corporate company. We're based out of North America. We were founded in 1982, and over time that's expanded out. We now got around 2,500 employees around the world, and I think we have regional offices in about 12 different countries, and a sales presence in around 140. So we are a large company. As such, our overall purpose, I suppose, or the mission statement that underpins the company as Neogen is around fueling a brighter future for food security. And within that, there are three key arms to the business around the improved food safety, so hygiene and testing for allergens and those type of things. Around enhanced animal safety, so we do a lot of things in just simple things like detectable needles and things that are safer going through the production chain. And obviously the area which I'm here to talk to you about, which is the area which we operate predominantly out of this part of the world, is around increased output via genomics. So that's a bit of an overview. From a genomics perspective, we have a global presence, so we do work all around the world in the genomic species. Our major kind of, I suppose, focus in genomics is around livestock and also companion animals, so dogs and cats and those type of things. We have in the past done a little bit in kind of the pigs and the poultry industries and a little bit in human genomics, but predominantly livestock and companion animals is our major focus. Actually, we've got labs in 5 different countries, and we're quite blessed from an Australian perspective that one of those labs happens to be just here at Ipswich, and somebody came through yesterday, but we are, I suppose, quite blessed as an Australian industry, as the livestock industry, to have a facility right on our doorstep here, and it's a world-leading type of facility in our backyard that was opened in 2022. And so this facility as such, just looking at that, so our presence in Australia and our laboratory in Australia, as many of you will be aware, kind of was purchased from the University of Queensland. It was previously the AGL lab there, based out at Gatton. So we purchased that laboratory in 2017, and then in 2022 we moved into our current facility as per the picture on the screen here. So it's been a big period of growth, and that's probably reflective, I suppose, of the growth in genomics, which is kind of and the technology which has happened during that time as well. And now we sit there as a local presence with around 90 different employees in Australia and New Zealand, and processing around 60,000 samples a month through the lab here. So that's, and most importantly, I suppose, from this side of things, we are very proud, if you like, of our partnership with ABBA, both currently through Neogen and also predecessing through UQ, in being able to provide genomic technology to you as Brahman breeders and members of the association. So that's something which we are really proud of and look to really extend and expand that into the future, so that we can all collectively, I suppose, get the most out of this technology. So that's the kind of, I guess, the overview of Neogen as such. What I would like to talk to you today about, to give you a bit more insight into genomics, is to go back and first of all just review the role of genomics and what value, I suppose, it's providing to us within our beef breeding businesses. Outline how genomically enhanced EBVs are calculated, discuss, I suppose, what it means for you, and then also give you a bit of an insight into where we might be going with this technology into the future. So to start off with, one of the things I often think when we stand up here and we start talking about the latest kind of tech and science and technology that's available to us, is we often forget to go right back and just remember what problem we're actually trying to solve with that technology. So we get caught up with its bells and whistles, but just forget about fundamentally what's the value that it's trying to provide and what we're trying to do with that technology in our operations. So if we go right back to, I suppose, first principles as such, that if we're trying to just improve the profitability of a livestock enterprise, be based up here in a Brahman program in Queensland or the Territory through versus an Angus program in Southern Australia, etc. There are a couple of major levers that we can pull if we're trying to improve our profit. And that's through a combination of both, first of all, breeding better animals and improving the genetics of those, through to then, I suppose, our management and how we feed those genetics so they can reach their potential. So we have a whole, those two major levers, I suppose, and the key to maximising our profitability is if we're moving both of those at the same time and extracting not only through gains in how we feed and manage those cattle, but also in terms of the genetics we're putting into those production systems. And obviously the genomics is fitting into this breeding better animals component. If we start to look at, then again, I suppose, what's the key and the key components of a successful breeding program? And again, we're trying to keep this fairly simple, but there are a couple of really key components that we need to address within our programs. The first is we need a really clear idea of what we're trying to achieve when we're making selection decisions. So we obviously need a very clear breeding objective, a list of breeding goals. We then need an idea of how we're going to achieve those goals in terms of the design of our breeding program. So we need to have an idea of what breeds are we going to use. We're going to run a self-replacing or a terminal type of breeding program. Are we going to have straight bred or crossbred type animals into our system? And then there's also the who component. So the what, the how, the who, and the who is really around then what animals are we going to select and use from the candidates that we have available to us to actually go through which one of those we're going to use in our breeding program, and how we're going to mate those, how we're going to allocate those between sires and dams. So we've got the what, the how, the who, and really where we're talking about genomics, it's in this who component as to where it's trying to help us. So within all of our, when we start looking at our animal selection as such, then we have a whole range, I suppose, I've skipped over a slide there, a whole range of different tools available to us to assist us with those selection decisions. So in our beef breeders kind of toolkit, if you like, we've got a whole range of information in terms of our bull soundness information, our visual appraisal of those animals and assessment of their phenotype, through to objective measurements and raw data, and then on to breeding values and selection indexes. And where genomics is really fitting in is it's representing the next generation of technology. So we're taking what those tools are, I suppose, and it represents a step change in what we have available to us to enable us to make more accurate and better selection decisions when we're trying to identify those animals with their genetics which are most aligned with our breeding objective to put into our breeding program. I think it's also important when we start looking at this just to reflect on the role of breeding values, because really genomics, if we simplify, and I'll give you the take-home message, I suppose, out of a lot of what I'm going to talk about today, is it's just giving us more accuracy in our breeding values. So it's important to reflect and think about, well, why do we actually have breeding values in the first place? Why are they advantageous to us, and what value are they providing? So when we're selecting an animal, obviously, the objective of what we're doing when we're making our breeding selection decisions is ultimately not necessarily just select the most superior animal, but to select the animal which is going to have the most superior progeny. So we're really interested in those with the best genetic merit. But the problem is, how do we actually identify those animals with the best genetic merit? The superior animals, those that carry genetics which are most aligned with our breeding objective, irrespective of what that breeding objective is. And there's a whole range of reasons why it's difficult for us to see that. So a lot of things that you'll be very familiar with, but in terms of when we're looking and assessing phenotype of animals, then only a component of that is due to their genetic merit, and therefore only a component of that is passed on and expressed in their progeny. It's not necessarily what you see is not what you get. Some traits are very difficult to see or to measure. So when we start looking at marbling, for instance, it's very difficult to assess that phenotypically. So we need to try and use some raw measurement and some technologies to try and have a look at that. Some traits are only expressed in certain sexes. So if you like, female fertility is not obviously expressed in our males when we're trying to make selection decisions. A lot of traits aren't measured prior to us making our selection decision. And of course, it's also very difficult to compare the genetics of animals which are running in different kind of environments. So this is really where breeding values and what the role they are is trying to solve some of those problems through science so that we're putting breeding values alongside those other tools in our toolkit to go through and ultimately identify those animals with the best genetics for our breeding program. And this is where genomics is coming in. The genomics component is just the next generation, I suppose, of creating and calculating breeding values. So when you talk about what genomic selection is, it's really around just going through and utilising information from an animal's DNA profile to kind of predict or improve the prediction of its breeding value. So in essence, if you like, about where that kind of DNA profile is, if you think about your animal that's sitting out there in the paddock, that animal is just made up of a lot of cells, and within those cells is a cell nucleus. And through technology today, we can take a sample, be it a tail hair or a tissue sample, and through the lab we can break that down, extract that DNA out of the nucleus of those cells, and then analyse and read that DNA, and it can help inform us about the genetics which the animal is carrying. So there are 4 kind of key steps in that kind of chain, if you like. So we have the collection of the sample on farm, which you're doing, and as we talked about, the 2 major types available to us in beef are our hair samples or our Orflex tissue sampling, our kind of ear notches to collect a tissue sample. They go through the lab, and importantly, the key part, and often misunderstood part about genomics, is all that we're doing in the lab is going and reading the DNA code. So the DNA code itself is ultimately just a series of A, C, T's and G's, if you like. It's an alphabet of, and it's different sequences of those A, C, T's and G's. All that the genotyping component that happens in the lab is just reading that DNA sequence. It's not actually informative about what the genetics the animal is carrying. We don't become informative until we go through and put that through a genetic evaluation such as breed plan, where it then interprets what those A, C's and T's, G's mean, and helps to predict the breeding value. And then, of course, the last and most important step of the whole process of genomic selection is actually using that information in the selection of our breeding animals. So if we're not using it to assist with our selection decisions, then we're getting no benefit out of genomic selection itself. So what's the value proposition, and why I suppose is the technology important to us? As we've talked about, it's really about us being able to make more accurate selection decisions. So by including genomic information alongside the other information which we have available into our genetic evaluations, we can get more accurate breeding values and make faster genetic improvement as a result. It also enables us to make selection decisions early in life. So in essence, you can consider genomics is a little bit akin to being able to take a DNA sample on a calf as early as the day of birth, if you like, put it through the lab, and it's equivalent to getting progeny information on those animals, a certain number of progeny with performance. We can now start to extract that information early, very early in the life, and be able to make those selection decisions with a lot more confidence at an earlier age. It also gives us a bit more flexibility than if we have to make management decisions, so things get tough and we have to make selection and culling decisions earlier. We've got more accurate information than we would have previously had available to us. It's also, and I think this is the area which we haven't quite really started to harness yet, but we will over the next 10 years, we will start to really see the benefits of, is being able to select for additional traits. So traits which we previously weren't able to measure on farm, but were still important and had an important impact on the kind of profitability of our production systems and our beef breeding program. Before we couldn't really measure those on farm, but now we can measure those in a genomic reference population and then make selection decisions on them. And that will then enable us to really improve in those traits areas which we weren't previously able to make selection decisions for. And the last one is really around, I suppose, the animals in which we can now have breeding values available to us. So previously, I suppose, we were very limited to having breeding values available on our seed stock animals, where they were, and those seed stock animals which had some performance data collected and often had a pedigree and a date of birth and those type of things available. Now through genomics, we don't necessarily have that same reliance on those kind of things which were a bit of a barrier in some cases before. So we can start to calculate breeding values without pedigree information, without birth, date of birth type of information, and actually start to really expand out the number of animals which have breeding values, and therefore the accuracy of our selection decisions, not only in our seed stock operations, but also in our commercial programs. I think it's equally as important to talk about what genomics is not. So a lot of people, I suppose their genomics, a lot of their background and their training comes from watching kind of crime shows on television like CSI, where we get the hint of a hair somewhere in the corner of a room and we can suddenly decipher that, and it tells you everything about everything that you ever wanted to know. So it's important also to acknowledge what the limitations of genomics are as such. First of all, genomics doesn't replace the need for breeding values. It actually, as I've talked about a lot already, it's about enhancing the breeding values that we have available and making them better. When genomics first started to come out, I think there was a lot of people who were optimistic that may not have been the best advocates of breeding values, that suddenly DNA was going to come in and replace all of that nonsense, and we'd be able to do DNA. That's not the case at all. So it's really about genomics and the breeding values going arm in arm, and it's about enhancing the information that we have available to us. The second thing, which is often misunderstood, is we don't actually know the genes yet. So when you're taking a DNA sample, all we're doing is we're going through and we're reading the DNA code, but we don't know what that DNA code means, in terms of we don't know within it where the genes are in general, and all our selection at the moment is still based on gene markers. So by a gene marker, really a particular segment of the DNA code or a portion of that DNA sequence we know might be associated with differences in a particular trait. So we might have animals that have a particular DNA sequence at that location in their DNA are associated, on average, tend to have higher growth rate, but we don't know if that's actually a gene for growth rate or what the impact is. So we're not actually dealing with the genes themselves. And it certainly doesn't replace the need to collect phenotypic measurements. In fact, the whole basis of genomics is related to actually having performance measurements recorded in what we call a genomic reference population. So first of all, it doesn't replace the need to, I suppose, collect information on farm. The more information you've got, the more accurate your breeding values are still going to be. So the more phenotypes you collect is still going to be important to that. But we also need that genomic reference population to extract information out of the genomics itself. And in other words, the actual having that DNA code itself is not informative at all, unless we also got animals which have got performance measurements associated with that, so we can work out the relationship between the two. So this is just, I suppose, expanding on that when I talk about what a genomic reference population is, and I think this is a really, if nothing else you walk away from today in terms of how genomics works, it's all around and underpinned by what we call this genomic reference population. So this genomic reference population is just a group of animals, if you like, which have both DNA information and comprehensive performance measurements. And so that is the ultimate, I suppose, resource on which we can start to use, and then we by understanding the relationship between those genomic profiles and those performance measurements, we can now start to take a genomic profile on these animals and then use it to produce a predicting value based on this reference information that's available to us. Without that reference population, then really this genomic profile is not informative at all. And likewise, the accuracy in which we get from genomic prediction varies very much dependent on the nature of this genomic reference population that's available. So if we look at things like the greater the size of the genomic reference population, the more accuracy we're going to get from genomics. The heritability of the trait, so traits which are less heritable, we need a bigger relative reference population to get the same level of accuracy out of our genomics than otherwise we would. So things like female fertility, we need a far bigger genomic reference population than we might for some weight and some growth traits to get the equivalent level of accuracy. The effective population size, and by effective population size I mean, well, how actually genetically diverse is your population of animals? So if we have a fairly narrow genetic pool, then when we test these animals, they're generally fairly closely related to the animals in the genomic reference population. So we can get more accuracy out of that prediction. In quite a, I suppose, genetically diverse breed, such as the Byrne breed, then you need a relatively larger size genomic reference population to actually get the same level of accuracy out of that. And also it's important, of course, that the reference populations which we're utilising are relevant to the production system of the animals in which we're trying to select. So we could go and develop a genomic reference population in a totally different production system, but it might not necessarily be reflective of how the animals are going to perform in the production system which we're running here. And in the case of, I suppose, industry genetic evaluation, such as your Byrne breed plan genetic evaluation, that genomic reference population is actually composed of any animal which has both a genotype and a phenotype available to it, or a performance measurement. So if you're participating in Brahman Breed Plan and doing genomics and collecting some performance measurements, then you're actually contributing to that genomic reference population. And then there's also the big part of that genomic reference population, particularly for the harder to measure traits which aren't as well recorded on farm. That genomic reference population is really made up of things like the Brahman bin and the repronomics programs. And really the key and a lot of the value, I suppose, that the Brahman breed is now able to extract out of genomics is entirely to do with the previous investments which have been made in those type of programs, and they will be extremely important to get that ongoing kind of value-added genomics into the future. So if we move now, I suppose, to a little bit more about exactly how EBVs are calculated within the black box, so within the calculation of breed plan. And if we look here, and I'm trying to, I suppose, again, simplify this in terms of the concepts behind this and trying to understand what is actually an extremely complex scientific model. But like anything, if we explain it in pictures, it seems to be a little bit more easy to understand rather than formulas. So if you think about a traditional breeding value as such, in terms of what we've had available to us since the 1980s, is there was pedigree information available to us and performance measurements. They went through a kind of genetic evaluation engine, and we got breeding values out the other end, and then we used those EBVs in selection to make genetic improvement. With genomics, very simply, all now is we've got a bigger and better engine available to us. So we've got a far bigger and better genetic evaluation engine, which is referred to as kind of single-step genetic evaluation. We're now, as well as we've got pedigree information feeding in, performance measurements feeding in, as we always have, but now we also have genomics feeding in as an additional source of information. We've kind of upgraded from a 4-cylinder to a kind of V8, and we've now got EBVs and exactly the same process, enable us to make selection tools and then harness that through making genetic improvement. And really, with a bigger and faster engine, all it's allowing us to do is to go faster. So to select on more traits earlier and really ramp up our genetic improvement. So how do we do, if we break that down and what actually happens within the engine, I suppose, it's what's actually how we use that genomic information. Again, if we break it right down to first principles around when we're actually calculating a breeding value, how is that done? And there are two key steps, I suppose, when we go to calculate a breeding value in these evaluations. The first one is we need to understand the relationship between the animal which we're trying to calculate the breeding value for and all the other animals in the genetic evaluation. So we need to know who its relatives are, and then we use the performance information which has been collected on those animals, on the animal and its relatives, to actually estimate its breeding value or predict its breeding value. And obviously the more closely related an animal is to the animal in which we're trying to calculate the breeding value for, the more impact that performance measurement has. The main impact of what genomics is doing is around how we estimate the relationships between animals. So prior to genomics, the relationships between animals, when we're doing that first step of understanding how related an animal was to other animals in the analysis, it was all based on pedigree. So the pedigree which was recorded enabled us to know how related an animal was to its grandparents and its half-siblings and all those type of things. And then that was used to kind of weight, I suppose, the performance information which was collected on animals when it was trying to calculate the breeding values for this animal. As we enter a genomics world, really in a single-step genetic evaluation, and there's several different, I suppose, approaches to actually using the genomic information, but the one that we use in Australia in the breed plan analysis is a relationship-based approach, where all we're doing now with the genomic information is really better defining the relationships between animals. So pedigree is still used when defining those relationships, but predominantly now it's looking at the genomic information. And why is that a benefit, I suppose? There are two major reasons. The first of all is it allows us to have more precise pedigree relationships. So before, the relationships we were using were kind of on average, if you like, that we expected an animal on average to have 25% of genetics in common with each of their grandparents. But due to the nature of Mendelian sampling and the kind of different mix of genes that we inherit over time, that's not actually exactly the case. So on average, they'll have 25%, but there's variation between that. So some of our animals will be more closely related to, say, their maternal grandsire than their paternal grandsire, etc. And before we didn't know about that. With genomics, we now do, and we've got more precise relationships, if you like, in terms of how we can go and then use and weight the performance information collected on those animals. The other main benefit is it also now enables us to determine the relationship between an animal to all those animals in that genomic reference population. So we've got this genomic reference population, which might be many, many thousands of animals, which have got really comprehensive performance measurements. There might not have been a known relationship between those animals based on the pedigree which we've collected, but there'll be genes in common and they'll share a relationship to those animals. Might not be as strong as it is to their close relatives, but we can still, nonetheless, it's informative to what their breeding value is. So now we can actually effectively, through genomics, come up with a relationship with these animals in the genomic reference, and that's akin to having additional relatives, if you like, and more information that we can use to calculate the breeding value and hence more accuracy. So you can consider the genomic reference equivalent to having more progeny, if you like, or progeny information on those animals, and by nature of the size of it, then it actually contributes quite a lot of information. This is a practical example. I didn't have a Brahman example, unfortunately, but to give you an idea of, in reality, what the variation in the relationship between animals actually looks like. So this is a sire, a very well-used sire in the Angus breed, has 2,500 progeny, Millimara paratrooper. And this is just showing, again, this graph here, the relationship between amongst all the half-sibs, so all paratroopers' progeny, I suppose. They're all out of different dams, but half-sibs, we expected before they'd have 25% relationship to one another, but some half-sibs are a lot more closely related to one another than they are to others, and likewise others are more distantly related based on the nature of the mix of the genes which they've got. Likewise over here, in terms of his relationship, paratrooper's relationship to his own progeny, on average we expected 50% of kind of relationship, 50% of genes in common, but there's actually variation around that based on the nature of the mix of genes that they've got. So before we didn't know this, we just assumed it was all 0.5 and all 0.25. With genomics now we've got a lot more precision around actually how we use this information. It's all good to have all this stuff, I suppose, in theory, that it all works in theory, but we also need to go through and make sure and check that that's actually working in practice. And the Animal Genetics and Breeding Unit have done a lot of work, I suppose, in recent time, actually going through and validating the extra, and I suppose validating is one word, but just really quantifying the actual value that we're getting from genomics in our evaluations. So this was a project which David Johnson has been mentioned a couple of times today, that's familiar to a lot of you, led. I presented this paper at ABBG. It's a major genetics conference in Australia back in 2023. But in this project, he went through and effectively adjusted the analysis, where he went and took all the performance data of animals in the last couple of years and removed it from the analysis and calculated breeding values for the kind of parents, and then looked at how those EBVs kind of related to the actual performance information which was collected on those progeny. So did the EBVs, and he did it both with genomics and without genomics, to see, well, when we put the genomics information in, would it have actually then better predicted the performance of those progeny that we saw. And here, if we like, effectively the take-home analysis has confirmed the theory as such that the EBVs were more, with genomics, were greater aligned with the animal's true breeding value or the performance of those progeny. So we got far greater predictive ability with genomics being used in the calculation of the breeding values than without it. But importantly, I suppose, the increase in the predictive ability really varied, and it really varied not only across breeds, but within breeds based on trait, depending on the size of the genomic reference population. So if we look here, the greatest benefit from genomics was in the Angus and the Wagyu breeds, by simple nature of they've got larger genomic reference populations. Brahman was sitting here nicely at, I think, around 0.13, 0.14, so at 13 to 14% additional predictive ability of the breeding values with the genomic information. But that also varied very significantly by trait as such. So when we go across the traits, there were some traits in gestation length where genomics wasn't providing much additional value, and I haven't actually gone and looked at the Brahman data, but I assume it's due to the small size of the genomic reference population, because it's quite a heritable trait, whereas other traits were actually quite a large improvement in accuracy. And the one that probably sticks out there to me is day-to calving, which obviously is one of the most important traits in terms of female fertility in all your indexes and a lot of your selection decisions. And genomics was providing the most accuracy, additional predictive ability, I suppose, for that particular trait, and really showing the value in Brahman. Likewise, with some of our growth traits, it was also increasing the predictive ability a lot. So for the key traits in which we're probably making selection decisions on in the Brahman breed, genomics was currently providing a lot of improved predictive ability. I will also not do that. That one down there. I would also, there's a bit, there are some improvements. This was back in 2023. There are some upcoming improvements that will be made to how genomics is utilised in the Brahman breed play analysis, which will further increase this predictive ability. So that's been rolled into some of the other breeds in recent times, and it has had a significant improvement again, and we'd expect to see that in Brahman in the not too distant future as well. I suppose the greatest demonstration we can have of what the actual value of genomics, the potential that it could provide to us, is I thought it was useful just to look outside the beef spear for a little while. And it's a slightly dated slide now, but just shows that the kind of impact that genomics has had in the North American dairy industry. So the dairy industry particularly was a really good candidate for genomic selection because it took a long time for them to kind of prove and get milking records on all the daughters of bulls and things when they were making their selection decision. So they've been able to shorten their gestation length quite significantly. But you can see here that the top graph is just showing the massive amounts of genotyping which is happening in the first place. So at the time of putting this slide together, I think it was about 12 months ago, there was greater than 6.5 million animals with genotypes in that genetic evaluation in North America. And they're genotyping about an extra million animals a year. But importantly, if we look at their genetic trend, from when they first introduced genomics back in 2009 through to now, and they've basically doubled their rate of genetic improvement through the use of genomics. So it's just obviously it's not necessarily relevant to beef directly, but shows what the potential of the technology is and how it's been harnessed in other breeds, in other species, other industries in other countries. So what does that all mean for you, I suppose? We've got genomics, the technology is now available. As I've shown you, it's been shown to have benefit. What does it actually mean for you when you walk away from here and say, well, what am I going to do with genomics? And how am I going to harness that within my breeding programs? The first thing is pretty simple. When you're making your selection decisions, I suppose, if you want to make the most accurate selection decisions, then incorporating genomically enhanced breeding values into your selection is the way to go. So even if you don't do any genomic testing yourself on farm, ensuring that you're first of all using breeding values, but ideally using the best possible breeding values as part of your selection by using those that have got genomics will give you the most accurate selection decision and therefore the most, most genetic gain out the other end. And how to tell that is when you're looking on the Brahman Association website and looking for information, you've got the traits analysed, and if they've got genomics in there, they'll have this genomics kind of clearly identified. The second thing is really from a seed stock producer perspective, I suppose, thinking about, well, how am I going to get the best out of genomics, and how am I going to develop a genomic testing strategy for my operation? So ultimately, I suppose it'd be nice to put up a really simple guidelines here for you, but the best utilisation of genomics is going to differ from herd to herd. There's no doubt about that. There's no one simple answer. So it's really working about what happens specifically for your operation, how it best fits within your overall management and your overall breeding objectives and how you do things. So coming up with your strategy about when and how you're going to collect your samples, which product are you going to utilise, what animals are you going to genotype and when, are all part of the questions in which you can help to guide through and answer. And there are people available to I suppose, assist you with that. So there's staff at Neogen, for instance, or at the Brahman Association, Paul, at the back of the room at Breed Plan, that can help you actually come up with that kind of genomic testing strategy for yourselves. So and the technology is also moving extremely quickly. So one of the things I'll be saying around your genotyping is to continually to check in annually and check where technology's gone and coming up and make sure you're keeping it up to date. The best practice, I suppose, and it's easy for me to say this now working for Neogen as such, but is to go and genotype all your animals. That's obviously going to give you the most additional kind of accuracy out the other end. For a lot of people that won't be achievable, there's a cost associated with it. So it's really around going through and starting to prioritise with the most influential animals in your breeding program, starting with them and then working your way up. So be it starting with your sires or your donor dams in your ET and IVF programs, through to maybe your replacement heifers, and then through to your sale animals, through ideally all calves out the other end. So that's kind of, again, there's no simple guidelines around this. It's about working what works for you within your breeding programs. I will say also just a few kind of hints or tips, if you like, about when you're actually collecting your samples, because there's a few common areas where people go wrong on farm and therefore don't get the most benefit out of genomics. The first one is to collect Orthoflex tissue sampling units. So hair has been a traditional way, I suppose, of collecting a DNA sample, but it's got some challenges around it. And now with Orthoflex TSUs, it's so much easier. There's a little bit of equipment involved in terms of the pliers and the actual TSUs themselves, but I really highly recommend you go through and start to use TSUs, because it not only is easier on farm, but it gives far better lab performance. And those of you who would have gone through the lab yesterday would have seen some of the automation and things that come across with it within the lab, which improves your turnaround times and those type of things. Really simple things, but things that people often stumble with is taking care to actually write down the tag number correctly, or make sure you scan it properly and with your kind of technology you have on farm, and then making sure that once you've correctly recorded the ID that you actually take the sample from that animal. So it's easy to get things mixed up. We've seen plenty of cases where samples have got one out and we go 50 animals before people pick up that we're out of sequence, and obviously when that goes into the genetic evaluation, there's no real way of working out you've made that mistake after the event. So actually collecting on farm and taking time to do things properly is really critical to getting good results. And the last one, of course, human nature is not to be organised. We've all got a lot going on, but the technologies you would have seen in the lab yesterday, for those of you who were there, is not something that can be turned around really quickly. So no matter how much you jump up and down and try and push it through the lab or want to pay extra, it's just this chemistry behind DNA testing doesn't enable it to happen. So really being organised and planning ahead and understanding the timeframes, within the lab, that kind of 4 to 6 weeks is needed, and then obviously it has to go into a genetic evaluation, and depending where you fit with kind of submission times, and that can be a month to 2 months to actually get EBVs back out the other end. So it's really important to think ahead and get yourself organised and think about where that sits within a breeding program. Lastly, just to, I suppose, give you some insights into where things are likely to go into the future. The first thing, I suppose, and where we haven't really seen it yet, we're starting to see some of the things, and Brad pointed out, I suppose, some of the research that was happening in the southern multibreeding and repronomics around the newer traits which have been collected. I think over the next 5 to 10 years, we're going to start to see what I'm calling next generation traits starting to come through and being available to us to make selection decisions. So traditionally, our selection, I suppose, is really focused on traits associated with production that we can measure on farm. Now I think we're going to start to really move into traits which aren't routinely measured on farm, those that are probably more associated with welfare and sustainability rather than necessarily straight production, things like feed efficiency, methane, immune competence and disease resistance and heat tolerance, and those type of traits will start to become available to us to incorporate in our selection decisions. The next thing, which is genomics, is really starting to change, and you will have seen some of this up here with Ben Hayes and the Northern Genomics kind of project, and now the availability of Repro BI. But we're now starting to get genomics tools available for, I suppose, unregistered and commercial animals. So Repro BI is probably the one that's most familiar to you, that is available through Black Box and genotyping, proudly done by Neogen. But we also have a range of different tools in Southern Australia now, which you might not be as familiar with, but there's a selection tool for Angus heifers, for Wagyu steers when they're entering into the feedlot, to actually take a DNA profile and get a picture of what their genetics are and whether they're suitable for that long-fed program. And then again a heifer selection type tool for crossbred Bos Taurus type animals. So the range of tools that will become available, I suspect, will really continue to kind of expand into the future. And people now in commercial setups and unregistered setups will have breeding values available to select their animals on. Another one which is a little bit more controversial, I suppose, or in some cases, is we'll start to use genomics for additional purposes. So start to use DNA to actually start to predict breed, if you like, or confirm breed, I suppose, in a lot of cases. And depending on the production system, that could have a range of different benefits in terms of not only within, say, the Brahman herd book as such, and being able to provide some additional integrity to that information, some additional kind of quality assurance, but then in terms of brand-based type of supply chains, so particularly say in brands like Angus and Wagyu, if they're Brahman branded products, etc., being able to validate those claims through DNA is now a kind of shortly to become a reality. And lastly, going a bit one steps. Lastly, in terms of the technology at the moment we've got is also evolving very quickly, and this won't affect you too much on farm as such, but actually behind the scenes, if you think at the moment, the underlying kind of genotyping platform which you're using goes through and measures the DNA of those animals at about 100,000 what we call SNPs or gene markers. There's new technology now that's coming down that's getting to a very similar cost point, which, for instance, we've got a new product which is still hasn't come into the Australian market yet, but in InfiniSeq, which now instead of 100,000 gene markers, we're talking about 2.2 million gene markers for the same cost. And feeding that into genetic evaluations and getting a more descriptive, I suppose, again, better definition of the genetics which animals are carrying and more accuracy out the other end. So that's, I suppose, all I really wanted to leave you with today. Just other than, genomics really, it's here. It's a step change in terms of the animal selection type of technologies which we have available to us. Ultimately, what the benefit of is it's enabling us to improve the selection of animals. The animals which we're selecting more accurately identify those which are aligned with our breeding objective and therefore make more genetic improvement out the other end. So it enables us to go faster. And from a breeder perspective, for bull breeders, really thinking about how you get the best out of genomics is something which I'd encourage you to do and to get across the technology. And to help you with that, I'm not sure if many of you know him as such, but Harry Stewart, who's at the back of the room, is our genomics territory manager here in Queensland. He works very closely with Marsha on a kind of day-to-day basis, and I'd encourage you, if you're looking at your genomic testing, to really get in touch with Harry as such, and he can come out on farm, sit down with you, talk you through the technology, come up with a strategy that assists you, and so that you can get the most out of the technology. So encourage you to, if you haven't met Harry, to introduce yourself to him, and if not, get in touch with him after the event, and he can come out and go from there. And while I'm talking him up a little bit, Harry's I will say, he'll be a bit embarrassed by telling you this, but Neogen, as you like, is a big global company, had a big awards ceremony in North America just a couple of months ago, or last month, and Harry was recognised for his great work over there, so he's kind of like our Reece Walsh, if you like, equivalent within our team. Thank you very much. All show, no go. Is that right?
Ben, do you have a question?
No,
Oh, sorry.
I'm leaving the comments a bit Harry. And the Reece Walsh.
Stu Wallace, question?
Andrew, could you just go back through the connection you've got with the black box, please?
Yes. So look, Black Box, that product was developed, I suppose, in the Northern Genomics project with Ben Hayes through UQ and in collaboration with MLA. At the end of that project, they licensed that technology to Black Box to commercialise to the industry. We have a relationship with Black Box where we do the genotyping, which feeds into the calculation of the breeding values in that program. So we're feeding in if you do your black box testing, I suppose you test through Black Box, those samples come to our lab and we genotype those with the same bovine 100K kind of platform, which is available in Brahman, but then that feeds through the kind of Northern Genomics prediction of the breeding values rather than, say, a breed plan in the breed plan side.
genomics, and relative to Angus and Wagyu, we had, 0.1
Less.
improvement, whatever. Is that related, and you referred to their larger reference populations, is it also a factor of their relative less diversity,
Correct.
say, than the Brahman as a breed?
Yes, yeah, it's a factor of all those combinations of things. So, but particularly, it's a nature, they've got a smaller effective population size, but then also generally have, I think I can say that with confidence, a larger reference population across most traits. I will say, it's not necessarily, the danger with putting up one slide with kind of the average in some traits. So dace carving is a good example. In the Angus breed, the additional accuracy is not nearly the same as what you're getting in the Brahman breed, simply by nature of the reference population that's available. So it's definitely, yes, the size of the reference population, but also the genetic diversity that you have available to you.
Any more questions for Andrew? Oh, you must have done very well, mate. Very well. Well, thank you very much.